Welcome to DAR Tutors for online and home tuition. Today, we will be diving into a fundamental and critical topic in IB chemistry higher level, acid-base equilibria. This video will provide a rigorous and comprehensive exploration of acid-base titrations, dissociation constants, buffer solutions, and the principles governing their behavior. We'll be working through several IB-style problems to solidify your understanding and refine your problem-solving skills. We'll begin with titration curves. Our objectives for this section are to define and distinguish between the equivalence point and endpoint, and to interpret titration curves to identify the equivalence point and buffer regions. A titration curve is simply a plot of the pH of a solution as a function of the volume of acid or base added during a titration. This tool is invaluable for studying neutralization reactions. It typically involves adding a titrant, which is a solution of known concentration from a burette, to an analyte, a solution of unknown concentration in a conical flask while measuring the pH. The titration curve provides a visual representation of how the pH of the mixture changes as the reaction progresses. By analyzing the curve, we can extract important quantitative information about the acid or base being studied. There are two crucial points we must differentiate: the equivalence point and the endpoint. The equivalence point is the theoretical point at which the stoichiometric amount of acid has exactly reacted with the stoichiometric amount of base. In other words, the moles of acid added are equal to the moles of base initially present and the reaction is complete. On a titration curve, the equivalence point is always located at the midpoint of the steepest, most vertical section of the curve. This point represents the greatest rate of change in pH for the smallest addition of titrant. Now, the endpoint is the point at which an indicator changes color. An indicator is a chemical substance, often a weak acid, that changes color over a specific pH range. Let's be clear about a common misconception. Indicators do not participate in the neutralization reaction. They do not help with neutralization. Their role is purely to signal a change in pH, specifically that the pH is within their color change range. An ideal indicator's color change range should correspond to the equivalence point of the titration. This ensures that the visually observed endpoint is a close approximation of the true equivalence point, allowing for an accurate determination of the unknown concentration. Now let's explore the four main types of titration curves, which depend on the strengths of the acid and base involved. Each curve has a distinctive shape. First, we have a strong acid-strong base titration. Let's consider titrating hydrochloric acid with sodium hydroxide. The pH starts very low because we have a strong acid. As base is added, the pH rises very slowly. Then there is a very sharp increase in pH over a small volume of base added. This is the equivalence point, which is at pH 7 for this type of titration, as the resulting solution contains only a neutral salt, NaCl, and water. Next, let's look at a strong acid-weak base titration. Imagine titrating hydrochloric acid with ammonia. The pH again starts low due to the strong acid. The curve rises slowly, then has a relatively steep section, though it is shorter than for a strong titration. The equivalence point occurs at a pH less than 7, making the solution acidic. This is because the salt-formed ammonium chloride, NH4Cl, hydrolyzes in water to produce hydronium ions, H3O+. Now let's switch to a weak acid-strong base titration. Here we might be titrating ethanoic acid with sodium hydroxide. The pH starts higher, around 3, because we have a weak acid that doesn't fully dissociate. There's the initial buffer region where the pH changes slowly, then a sharp rise. The equivalence point for this titration is at a pH greater than 7, making the solution alkaline. The salt formed, sodium ethanoate, hydrolyzes to produce hydroxide ions, OH. Finally, we have the weak acid-weak base titration. An example would be ethanoic acid with ammonia. In this case, there is no sharp pH change at the equivalence point. The curve rises gradually throughout. As there is no distinct steep section, it is extremely difficult to accurately determine the equivalence point, and therefore this type of titration is not used for quantitative analysis. In summary, the pH at the equivalence point and the shape of the curve's steep rise are determined by the strength of the acid and base being titrated. Identifying these features is key to understanding the reaction. Our objective now is to learn how to select an appropriate indicator for a titration. A suitable indicator changes color over a pH range that includes the equivalence point. Let's revisit our titration curves and consider which indicators are suitable for each. For a strong acid-strong base titration, the pH jump is very large, from about pH 4 to pH 10. Both methyl orange, which changes from red to yellow between pH 3.1 and 4.4, and phenolphthalein, which changes from colorless to pink between pH 8.2 and 10.0, are suitable indicators because their ranges fall entirely within the steep portion of the curve. Now, for a strong acid-weak base titration, the pH at the equivalence point is acidic, less than 7. A suitable indicator must change color in the acidic range. Therefore, methyl orange is a good choice. Phenolphthalein, on the other hand, changes color far too late, outside of the steep part of the curve. It would be impossible to determine the equivalence point accurately using phenolphthalein. Conversely, for a weak acid-strong base titration, the equivalence point is in the alkaline region at a pH greater than 7. Here, phenolphthalein is a suitable indicator. Methyl orange, however, would change color much too early, before the equivalence point is reached, giving an inaccurate result. And finally, as we discussed, no indicator is suitable for a weak acid-weak base titration because the absence of a sharp pH change makes an accurate endpoint impossible. Our next objective is to define the acid dissociation constant Ka and use it to calculate the pH of weak acid solutions. This is a higher-level topic. Remember that a weak acid HA only partially dissociates in water. This is an equilibrium process. The equilibrium constant for this dissociation is called the acid dissociation constant, Ka. It's defined as the concentration of products divided by the concentration of reactants, with liquids excluded. So, Ka equals the hydrogen ion concentration times the conjugate base concentration, all divided by the undissociated acid concentration. K is a quantitative measure of acid strength. A larger Ka value indicates a stronger weak acid, meaning it dissociates more in solution. Since Ka values are often very small, we frequently express them as pKa. pKa is defined as the negative logarithm of Ka. A smaller pKa value corresponds to a larger Ka value, and therefore, a stronger weak acid. To calculate the pH of a weak acid solution, we use the Ka expression. For a weak acid HA dissolving in water, we can make two key approximations to simplify the calculation. First, the dissociation is so small that the concentration of H+ is approximately equal to the concentration of AT. Second, the amount of acid that dissociates is negligible compared to the initial concentration of the acid, so the equilibrium concentration of HA is approximately equal to its initial concentration. Substituting these into the Ka expression gives us this simplified equation, which we can then rearrange to find the hydrogen ion concentration, H+. This allows us to calculate the pH. Let's apply these concepts with two worked examples. First, we'll calculate Ka from a given pH. The pH of a 0.01 mol DM3 benzene carboxylic acid solution, C6H5COH, is 3.10. We need to calculate its K value. Let's start with the equilibrium expression. The pH is the negative log of the H+ concentration. So, to find the H+ concentration, we take the antilog of the negative pH. This gives us 7.94 times 10 to the power of negative 4 mol DM3. Now we can use our approximations. The H+ and conjugate base concentrations are equal, so we can replace C6H5COO with H+, and the initial acid concentration is 0.01 mol DM3. Plugging these values into our equation and solving, we find that the acid dissociation constant, Ka, for benzene carboxylic acid is 6.30 times 10 to the power of negative 5. Now for our second example, calculating pH from a known Ka value. We'll use our simplified Ka expression and solve for H+. This is 0.0134 mol DM3. Then, to find the pH, we take the negative logarithm of this value. The pH of the 0.1 mol DM3 ethanoic acid solution is 2.87. Understanding the relationship between molecular structure and acidity is crucial. Let's examine the acidity of oxyacids containing a halogen. Consider chloric Y acid, H-alkyl, and iotic I acid, HO. HOCl is a stronger acid with a larger Ca value than HO. Why is this? It's all about electronegativity. When the hydrogen atom in an oxyacid ionizes, it leaves its electrons behind with the oxygen atom, forming a bond. The resulting negative charge must be stabilized for the acid to be strong. In both acids, the halogen atom, X, pulls electron density towards itself because it is more electronegative than the oxygen. Chlorine is more electronegative than iodine. Because chlorine is more electronegative, it pulls electron density from the oxygen even more strongly. This vacuum cleaner effect makes the OH bond more polar, weakening it and making it easier for the hydrogen ion to dissociate. Furthermore, after the H+ ion leaves, the resulting negative charge on the oxygen of the conjugate base, OClAc, is more spread out due to the stronger inductive effect of chlorine. A more stable conjugate base corresponds to a stronger original acid. Therefore, the increasing electronegativity of the halogen atom leads to a stronger acid. This principle allows us to predict relative acid strengths based on molecular structure. We've focused on weak acids. Now let's turn our attention to weak bases. Our objective is to define the base dissociation constant, Kb, and learn its relationship with Ca for a conjugate acid-base pair. Similar to acids, weak bases only partially ionize in water. Let's take a general weak base, B. It reacts with water to produce its conjugate acid, BH+, and hydroxide ions, OHE. The equilibrium constant for this reaction is called the base dissociation constant, Kb. Just like Ca, a larger Kb value indicates a stronger weak base. A crucial relationship exists between the acid dissociation constant of a weak acid and the base dissociation constant of its conjugate base. For any conjugate acid-base pair, the product of their dissociation constants, Ca times Kb, is always equal to the ion product of water, Ca. At 25 degrees Celsius, Q is 1.0 times 10 to the power of negative 14. If we take the negative logarithm of both sides, we get the simpler relationship that pKa plus pKb equals pKw, which is 14. This equation is extremely powerful. It tells us that a strong acid has a weak conjugate base, and a weak acid has a strong conjugate base. In other words, as the strength of the acid increases, its conjugate base becomes weaker, and vice versa. Now let's use Kb to calculate the pH of a weak base solution. We'll calculate the pH of a 0.5 mol DM3 solution of ammonia, NH3, for which Kb is 1.8 times 10 to the power of negative 5. This is a common IB-style question. First, we write the dissociation equilibrium for ammonia. Then we set up the Kb expression. Using the same approximations we did for acids, that the dissociation is small, we can simplify the expression. We can assume that at equilibrium, the concentrations of ammonium ion, NH4+, and hydroxide ion, OH, are equal. Let's call this concentration X. We also assume the initial concentration of ammonia, 0.5, is approximately equal to the equilibrium concentration. Plugging these into our Kb expression, we solve for X. This gives us the hydroxide ion concentration, which is 3.0 times 10 to the power of negative 3 mol DM3. Now we can calculate the pOH, which is the negative log of the hydroxide concentration. This gives us a pOH of 2.52, but the question asks for pH. Using the relationship pH plus pOH equals 14, we find the pH of the ammonia solution to be 11.48, which is consistent with it being a base. We must also consider the pH of salt solutions. Our objective is to explain salt hydrolysis and use it to predict the pH of a salt solution. Not all salts dissolve in water to form neutral solutions. Some undergo a reaction with water called salt hydrolysis. Salt hydrolysis occurs when an ion from a salt, which is the conjugate acid of a weak base or the conjugate base of a weak acid, reacts with water to produce H+ or OH ions. This changes the pH of the solution. Let's look at the 4 types of salts. First, a salt from a strong acid and a strong base, like sodium chloride NaCl. Neither the Na+ cation nor the cell anion is the conjugate of a weak species. They are spectator ions, so the solution remains neutral with a pH of 7. Second, a salt of a weak acid and a strong base, like sodium fluoride NaF. The Na plus is a spectator. The fluoride ion, Fe, is the conjugate base of the weak acid HF. It is strong enough to hydrolyze. The reaction is FAQ plus H2OL in equilibrium with HFAQ plus OH-AQ. Excess hydroxide ions are produced, so the solution is basic with a pH greater than 7. Third, a salt of a strong acid and a weak base, like ammonium bromide, NH4Br. The Birgiusher is a spectator. The ammonium ion, NH4+, is the conjugate acid of the weak base NH3. It hydrolyzes to produce H3O+. The reaction is NH4 plus AQ plus H2OL in equilibrium with NH3AQ plus H3O plus AQ. Excess hydronium ions are produced, so the solution is acidic with a pH less than 7. Finally, a salt of a weak acid and a weak base, like ammonium ethanoate. Both the ammonium ion and the ethanoate ion hydrolyze. The final pH depends on the relative strengths of the conjugate acid and base. It can be acidic, basic, or neutral, depending on whether the pKa of the acid is less than, greater than, or approximately equal to the pKb of the base. Let's work through an example of predicting the pH of a salt solution, a common IB question. Sodium fluoride, NaF, is a salt formed from the strong base NaOH and the weak acid HF. We need to predict and explain the pH of its solution. A useful strategy for these problems is to identify the ions formed and determine whether they are spectators or if they hydrolyze. We must also identify whether the salt is from a strong or weak acid and a strong or weak base. First, the salt dissolves in water to give sodium ions, Na+, and fluoride ions, F-. Second, we analyze each ion. Na+ is the conjugate acid of the strong base NaOH. The conjugate of a strong base is extremely weak and does not react with water. So Na+ is a spectator ion. Next, we analyze the anion, F-. F- is the conjugate base of the weak acid HF. Since HF is a weak acid, its conjugate base F- is relatively strong. F- will hydrolyze. This hydrolysis reaction shows fluoride ions reacting with water to produce hydrofluoric acid and hydroxide ions. The production of excess hydroxide ions makes the solution basic. Our final topic for this part of the video is buffer solutions. The objective is to define a buffer solution, describe how it resists pH change, and calculate its pH using the Henderson-Hasselbalch equation. A buffer solution is a solution that resists changes in pH when small amounts of a strong acid or base are added, or when it is diluted. It doesn't keep the pH exactly the same, but it minimizes the change. Buffers are composed of a conjugate acid-base pair. There are two main types. An acidic buffer consists of a weak acid and its salt containing its conjugate base. For example, ethanoic acid CH3COOH and sodium ethanoate CH3COONA. A basic buffer consists of a weak base and its salt containing its conjugate acid. For example, ammonia, NH3, and ammonium chloride, NH4CCl. Let's see how an acidic buffer works using ethanoic acid and ethanoate ion. If a strong acid is added, the extra H+ ions react with the conjugate base ethanoate to form the weak acid ethanoic acid. This reaction removes most of the added H+ ions, preventing a large drop in pH. If a strong base is added, the extra OH ions react with the weak acid ethanoic acid to form water and the conjugate base. This removes most of the added OH ions, preventing a large increase in pH. The pH of a buffer solution can be calculated using the Henderson-Hasselbalch equation. The pH of an acidic buffer is equal to its pKa plus the logarithm of the ratio of the concentration of the conjugate base to the concentration of the weak acid. This equation is incredibly useful. It shows that the pH of a buffer depends primarily on two factors: the pKa of the weak acid and the ratio of the concentrations of the conjugate base and the acid. If the concentrations are equal, the ratio is 1, and the pH equals the pKa. This means that the pKa of the weak acid represents the central point of the buffer's effective pH range. A similar equation exists for basic buffers, but it's often simpler to calculate pOH using pKb and then convert to pH. Let's work through an example. Calculate the pH of a buffer containing 0.20 moles of sodium ethanoate in 500 cc of 0.10 mole DM3 ethanoic acid. The Ca for ethanoic acid is 1.8 times 10 to the negative 5. First, we need the concentrations of both components. The ethanoic acid concentration is given as 0.10. For the ethanoate, we calculate the moles and divide by the volume. It's crucial to convert the volume from CM3 to DM3 by dividing by 1,000. Next, we calculate pKa. pK is the negative log of Ca. For ethanoic acid, this is 4.74. Finally, we apply the Henderson-Hasselbalch equation. We plug in pKa, the concentration of the base, ethanoate, and the concentration of the acid, ethanoic acid. The calculation gives us a pH of 5.34 for this buffer solution. A key feature of buffer solutions is buffering capacity. Let's define this concept and see how it relates to titration curves. Buffering capacity is a measure of how much acid or base a buffer can absorb before its pH changes significantly. It's not infinite. Buffering capacity depends on the concentrations of the weak acid and its conjugate base. The more of each component a buffer contains, the greater its capacity to resist pH changes. This concept is beautifully illustrated by the titration curve for a weak acid with a strong base. At the beginning of the titration, before any strong base is added, there is only the weak acid, so no buffer exists. As strong base is added, some of the weak acid is converted into its conjugate base. A buffer solution is formed. The flat part of the curve indicates that the solution is now acting as a buffer, and the pH is changing slowly. At the midpoint of this buffer region, half of the weak acid has been neutralized. At this point, the concentration of the weak acid is equal to the concentration of its conjugate base. As we saw, under these conditions, pH equal pKa. This means you can find the pKa of a weak acid directly from its titration curve by locating the pH at the half equivalence point. The buffer region corresponds to the pKa of the acid, and the midpoint of this region represents its maximum buffering capacity. As we add more base, we eventually consume all the weak acid and the buffer breaks, leading to the sharp pH jump at the equivalence point. We have now covered the core concepts of acid-base equilibria. Let's recap what we've learned. We started with the fundamentals of titrations and titration curves, defining the equivalence point and understanding how to interpret the shape of the four main types of curves. We saw how the choice of indicator is crucial for accurate results. Next, we moved to the quantitative aspects, defining Ca for weak acids and Kb for weak bases, and learning how to calculate pH and dissociation constants. We explored the relationship between molecular structure and acidity, and discovered the vital link between Ca and Kb for a conjugate pair. Finally, we covered buffer solutions, which are essential for maintaining stable pH. We saw how they work by absorbing added acid or base and learned to calculate their pH using the Henderson-Hasselbalch equation. Mastering these concepts will provide a strong foundation for your IB chemistry journey. Remember to practice the worked examples and review the key equations. It's been a comprehensive session. For students seeking to truly excel in IB A-level and IGCSE curricula, expert tuition can make a significant difference in clarity, confidence, and achievement. If you're looking for personalized, rigorous, and concept-driven support, we invite you to contact DAR Tutors. Our team of experienced educators is dedicated to providing tailored guidance that helps students unlock their full potential. Now, let's put your knowledge to the test. Here are 5 IB-style practice questions with fully worked solutions to help you consolidate your learning. Take your time to work through each one. Question 1. A 0.25 mol DM3 solution of a weak acid, HA, has a pH of 4.15 at 25 degrees Celsius. Calculate its acid dissociation constant, K. Pause the video and try to solve it yourself before viewing the solution. First, we find the H+ concentration from the pH. Second, we use the simplified Ca expression for a weak acid. Plugging in our values, we get a Ca of 1.25 times 10 to the power of negative 8. Question 2. Which of the following 0.1 mol DM3 solutions would have the lowest pH? Ammonium ethanoate, sodium ethanoate, ammonium chloride, or sodium chloride? And explain your choice. Pause the video and consider the type of acid base that formed each salt. The salt that will give the lowest pH is ammonium chloride. NaCl is neutral, and NaCH3COO is basic. NH4CH3COU has a pH that depends on the relative Ka and Kb values, but it's generally around 7. NH4Cl, formed from a strong acid and a weak base, hydrolyzes to produce H+ ions, making the solution acidic and thus giving it the lowest pH. Question 3. A buffer solution is prepared by mixing 200 cm3 of 0.10 mol DM3 ethanoic acid with 100 cm3 of 0.10 mol DM3 sodium ethanoate. Given that the pKa of ethanoic acid is 4.76, calculate the pH of the buffer solution. Pause the video and apply the Henderson-Hasselbalch equation. First, we calculate the initial moles of the weak acid and its conjugate base. Second, we find the total volume. Third, we use the moles and total volume to get the concentrations for the HH equation. Finally, we plug in pKa and the concentrations. The pH of this buffer is 4.46. Question 4. 25.0. Cubic centimeters of 0.100 molar propanoic acid is titrated with 0.100 molar sodium hydroxide. Given that pKa for propanoic acid is 4.87, determine the pH at the equivalence point. Pause the video. Remember, at the equivalence point of a weak acid-strong base titration, the solution is basic. First, we find the volume of base needed. Second, we find the total volume at the equivalence point. Third, we calculate the moles of the salt produced. Fourth, we find the concentration of the conjugate base, propanoate. Fifth, we use the Kb for the conjugate base to find the pOH. Finally, we convert pOH to pH, giving a pH of 8.91 at the equivalence point. Question 5. Our final problem. A 20.0 cubic centimeter solution of 0.150 molar potassium hydroxide is titrated with 0.100 molar hydrochloric acid. Part A asks you to calculate the pH of the solution after 20.0 cubic centimeters of acid has been added. Pause and solve. This is a strong acid-strong base titration, but notice the different volumes and concentrations. Solution to Part A. We calculate the initial moles of hydroxide ions and the moles of hydronium ions added. We see that the moles of hydroxide are in excess. We then calculate the remaining concentration of hydroxide and find the pOH, which gives us a pH of 12.30. Part B asks you to calculate the pH after 30.0 cubic centimeters of acid has been added. Again, pause the video and solve. Solution to Part B. This time, the moles of acid added are in excess. We calculate the remaining H+ concentration and find its negative logarithm. The pH of the solution after 30 cubic centimeters of acid is approximately 1.60. This concludes our deep dive into acid-base equilibria for IB Chemistry HL. We've covered a vast amount of material, from the fundamental to the complex. Thank you for joining this DAR Tutors video. Remember, consistent practice and a clear understanding of the underlying principles are key to your success in IB Chemistry.